Hi everyone, welcome to week 8. This is Dr. Bertman. I'm going to be your host for right now as we move into the second half of our course. Up until this point, we've been looking at the scientific basis for climate change, what the drivers are, what the predictions are for future climate, what the consequences are for human and non-human health. We've looked at some of the social, psychological, economic, political challenges of acting to mitigate and adapt to climate change. What we're going to do in the second half is focus a little bit more on solutions. What should we be doing? What do we need to be doing? How do we bring it about? What are the best strategies? We're going to start at the beginning, looking at the major source of the pollution that causes climate change, namely from energy production. And we're going to see if we can figure out a way of is it possible to get to zero greenhouse gas emissions by 2050, as the IPCC suggests. This week, presentations are a collaboration between myself, Professor Pancella from the physics department, Professor Miller from the chemistry department, and we will be coming and going, so don't be too concerned. So energy is the largest contributor to greenhouse gas emissions, largely from the combustion of fossil fuels, as we have discussed. And so what we need to do is recognize that human activities are going to require energy for the things that we do, from powering up your cell phone to driving places to making things in industry. So we need energy, but we need to find energy sources that don't produce greenhouse gases. There are 6 major categories identified by the U.S. government for keeping track of production and consumption: solar, nuclear, geothermal, hydroelectric, wind, and biomass. I imagine that most of you are familiar with some or all of these sources. Nuclear energy, technically, some people would consider it to be renewable. It has its own issues. We're going to not talk too much about nuclear energy this week. We are going to primarily look at the other 5 categories, and you'll see those categories repeated in upcoming slides. Let's start by looking at a little bit of the history of energy use in the United States. Starting with the formation of our country and going into the middle part of the 19th century, we see that the primary external energy source is this yellow trace, which is biomass, primarily wood. Prior to this point, most work was done by the energy provided by muscle power, either human muscle power or animal muscle power. This external source describes the beginning of the Industrial Revolution, where industry needed external energy beyond what could be provided by muscle power. And most of that was provided by wood up until the middle part of the 19th century, where, as this black trace describes, coal started to be used. The y-axis, the vertical axis of this graph, is in units of quadrillion British thermal units, which is pretty much an arbitrary energy unit. You don't have to worry too much about it unless you become an engineer. But this is often abbreviated as quad. So this 45 here represents 45 quad of energy. And you can see up until the middle part of the 19th century, this country used less than 5 quad of energy per year. So this is annual energy consumption. So let's see, walk into the future and see what happens to the energy situation. from those two primary energy sources, that buildup of coal consumption in the middle part of the 19th century continued exponentially until the turn of the 20th century, when we discovered oil in our country. And then oil sort of took off as the primary source of energy, growing exponentially well into the 20th century. A couple decades after oil, natural gas came on the scene, and we can see now today petroleum, natural gas, and coal are the primary energy sources for everything that we do in this country. And they're all three of them are fossil fuel sources. And you can see that we use quite a bit more energy now than we did back 150 years ago. These the smaller categories are the other energy sources that we talked about. And up until the 20th century, they were essentially non-existent, except, of course, biomass. Hydroelectric power started to build in the 20th century. It grew steadily until the middle part of the 20th century, and then it has more or less plateaued. We've tapped out hydroelectric power. There's not a whole lot more that we can squeeze out of it. After World War II, nuclear energy took off, but it also has plateaued. The renewable sources that are the potential for growth is in this light green trace here, which up until the 21st century wouldn't have shown up on this graph at all. Biomass is still a significant player, but taken together, these pale in comparison to the amount of energy that we get from fossil fuels. So one way to look at starting to think about how to transition to non-fossil fuel energy is to look at how the energy is used. And this diagram, it's pretty busy, but it's known as a Sankey diagram that describes the flow of a quantity. In this case, it's energy. On the left-hand side are those sources of energy categorized that I described before. And each box is roughly the relative amount of energy that we get from each of those sources. Starting from the left and flowing to the right, these different bars indicate the relative amount of each of those energy sources that goes into end-use sectors. And there are 5 defined here: electricity generation, and then end use in the pink: residential, commercial, industrial, and transportation. So let's just note a couple of things. Petroleum is the primary energy source that goes into transportation. And transportation represents about a third, almost a third of our energy use, and most of that comes from petroleum. A small amount of petroleum is used for industrial activities. On the flip side, most coal goes into producing electricity, and very little of it goes into industrial, and none essentially goes into transportation. Natural gas is the fossil fuel source that is the most versatile, is used for electricity generation and for residential, commercial, and industrial use, primarily for producing heat. The renewable energy sources, the non-greenhouse gas producing energy sources, are small contributors, but mostly they go into producing electricity. So that's how to read this Sankey diagram. And I want to bring your attention to the gray boxes at the very end. This totals up what happens to that energy in 2 categories. One is rejected energy. What is rejected energy? It is wasted energy, energy that goes into the environment as heat without doing anything productive or producing any work. The actual energy used is described here in energy services, and that's less than a third of the total energy that we consume. So we consume all of this energy and use only a third of it. That's like filling your gas tank up with 15 gallons of gas and pouring 10 of it onto the road. It's a huge waste and a huge opportunity to improve our energy situation through efficiencies. This wasted energy is largely a result of the inefficiencies of burning fossil fuels. It's a very inherently inefficient process. A lot of the energy just produces low quality heat that can't be used for useful work. And so we can realize real benefits from improving efficiency. But it's not necessarily the energy that we're interested directly. What we want to know is where the carbon dioxide emissions come from. And as this additional Sankey diagram showing the same energy sources on the left-hand side shows what we pretty much already know, that natural gas, coal, and petroleum produce the lion's share of the carbon dioxide that goes into the atmosphere to produce global warming that creates climate change. The end uses of the CO2 emission comes from primarily electricity generation and transportation. So that's where we need to really focus our efforts. We need to figure out ways of producing electricity and transporting people and goods without producing greenhouse gases. So this graph shows similar data to what I've shown before, but in a different way. This pie chart represents the major categories of energy use as of 2019. Coal, petroleum, natural gas, fossil fuels provide about 80% of the energy that we use. Nuclear provides about 8%, and renewable energy, all of those types of energy grouped together produce about 11%. Now, fortuitously, the U.S. energy consumption is about 100 quad of energy per year, and so 100 quad, we can directly translate these percentages into absolute energy units. So petroleum provides 37 quad of energy. Remember, before the Industrial Revolution, the country used less than 5 quad total for the whole year. And now we get 37 quad of energy per year from petroleum alone. So that just hopefully gives you some perspective on the scope of our energy use. So let's look at our renewable energy portfolio. Let's break out that green wedge into the individual components. And this shows that the single largest contributor to our renewable energy portfolio is biomass, a fair fraction of which is wood still. We still burn a lot of wood, and it's a big fraction of our renewable energy portfolio. 20% of our renewable portfolio is from wood alone. A similar fraction from biofuels. After biomass at 43%, we go wind at 24%, hydroelectric at 22%, solar at 9%, and geothermal at 2%. So we ask ourselves a couple of fundamental questions. One, is renewable energy only 11% of our energy use because there isn't enough renewable energy available? Do the various categories, the amounts, the distribution of the different categories of renewable energy represent the total potential amount of energy that's available from those different sources? Are we doing as good as we can do? That's what we're going to explore next and for the rest of the presentations this week. Next up is Dr. Pancella.
But the potential is there. if you ask the question, would it be even theoretically possible to supply all of our present and for some time in the future energy needs in the United States with strictly renewable energy sources? Yeah, the answer is yes. The sun shines everywhere and drops a lot of energy on us, and it moves the air around. And if we decided to, we could harvest more than enough energy to cover our needs just from solar and wind. This table summarizes results of a pretty reliable 2012 study that evaluated how much renewable energy could be harvested just in the territory of the United States. And that's good news. This doesn't take into account, the costs, the economic investment that would be required. We'll talk about some of that as we go along. But the possibility exists that we could do it. The rate which we need to supply our current energy needs is only 3,400 gigawatts, and we've got that many gigawatts from a couple different sources as a potential. Okay, so now let's take a little closer look at some of those potential sources, and explain why I think some of those are more important than others. And we'll start from the right of that previous table. Let me even go back here and see if this works. So we'll start with biofuels, sometimes called biomass. We'll look at hydroelectric and various kinds of geothermal as we work our way toward these other familiar sources that have a lot of potential. We think we should continue using biofuels and biomass where that's practical and economical, and it's good, especially appropriate for heating in many contexts, modest amounts of heating. We use also biomass right now to supplement our gasoline fuels with liquid ethanol that's derived mostly from corn crops. That I don't think we want to expand a lot because, for one thing, we need corn for other reasons, and for another, the energy that you put into planting, fertilizing, tending crops, harvesting, processing the ethanol, that takes a lot of energy as well. So it's not really much of a net source of energy. So not a great benefit for the balance of impacting the climate. So we're not going to project much, if any, maybe even a decrease in the use of biomass overall. For hydroelectric, it's somewhat similar story. Hydroelectric power is a great source of clean energy. It can be harvested pretty continuously at a given rate for a given stream, of course, but it can be you can get that energy and deliver it without any greenhouse gases being emitted. So that's what's really good about it. But we have developed, in this country, we've developed hydroelectric power almost to the maximum we probably want to. I don't think we want to build a lot more dams and reservoirs to increase this source. We're already on the optimal sites. There's a lot of good reasons to keep rivers in their current state if they're not dammed up. You may have heard about the Kalamazoo River where dams are being removed. Wildlife, recreation, habitat. Habitat is changed a lot when you make a big reservoir. There are other competing land uses. There aren't that many good places where you could add more dams, maybe a few more in Alaska. But for these reasons and others, we don't think this source will be will be expanded a lot. The story with geothermal can be kind of confusing. Traditional geothermal power is harvested from the earth because deep down the earth is hotter, and anytime you have a temperature difference, you can exploit that to use that energy to make it turn it into mechanical energy, and for instance turn an electric generator and make electric power. And this has been demonstrated. It's done in certain sites. The places where it's economical and good to do are kind of unusual sites where the way the Earth's crust and fissures and faults are, hot parts of the Earth, hotter temperatures are located closer to the surface. If you've been out to Yellowstone National Park, that's one of these places, and weird things happen. And so these are the places where you can exploit this resource very well. But there aren't that many of them around, it turns out, that are really, really good. To expand this type of energy, you'd have to drill deeper and use more technology and more complicated things, and it would be more expensive, and it's not clear that's a really good way to go. And the other reason is kind of interesting to me. When people originally started doing this, they thought, well, the temperature down at this depth, at this location is what it is, and it'll always be that way. It's an unlimited heat energy resource. Let's just go get it and use it, and there'd be no problem. But it's not unlimited in the sense that the heat has to flow from elsewhere, from the center of the earth or from the surrounding rocks, and rock isn't a very good conductor of heat. And so when you start pulling that heat energy out, if you pull it out fast, the rock cools down and you can't pull it out as fast. And that's turned out to be the case, and that's made most of these sites less productive than originally thought. And so you get less energy than you thought you would for your investment in drilling the well and putting up the equipment. If you wanted to go someplace else, you'd have to spend more money. And so that's not a there's not, in our judgment, a lot of potential for expansion there that makes sense. This slide shows a few of the favorable sites and where they're located. But there's a lot of places where it's not favorable, and the good sites are actually fairly rare. So this slide, again, talks about that. I got a little bit ahead of myself on the audio part. Without going into much more detail, most people agree this is not a big future resource to expand and cover a lot more of our needs. There's another kind of geothermal power that some people are more familiar with, you might be more familiar with, that is not as expensive, not as elaborate, and doesn't require this deep drill. And that just exploits the fact that below ground, anywhere you are, you don't have to go too far down before the temperature stabilizes and is year-round at about 60-some degrees Fahrenheit. And it means in the winter, you can bury some pipes, and you can circulate some fluid like antifreeze, and you can extract that heat energy. It's much lower density heat energy, but it still can be extracted using a heat pump, which is just like what's used in a refrigerator. And you can warm up some air or warm up some water for your use in your home or reasonable sized buildings, and that works pretty well. And it's another fairly carbon neutral way of supplying some energy to use for heat. And there's nothing wrong with it. But again, it's probably not going to be a huge source of energy on a large utility scale, like for industry and transportation and all the other things we use energy for. But it can make a contribution for home heating and space heating at a modest scale. In fact, we are doing it here at Western Michigan University with our new Alumni Center and the Zhang Legacy Center, where the archives are on our East Campus. And it can be a reasonably good way to go if done well. It's fairly expensive relative to other forms of space heating today, and so that's another reason we don't think it's going to be easy to expand it a lot, but it will have a place. So on the large scale, when you're talking about the thousands of gigawatts or the 100 quadrillion BTUs of energy that we use per year, we need to be talking about the things further on the left on our previous table. The solar power and the wind power, which can be exploited at a larger scale. Again, though, with little climate impact. So those are the things that I'm going to count on and recommend that are in the mix in 2050, including nuclear fission. Yeah, that's the kind of nuclear power we have nowadays already. Nuclear generating plants are already generating electricity, supplying the grid all over the country. About 100 nuclear power plants in this country right now, many in other countries as well. And while some people have issues with nuclear power, the threat of climate change on a global scale means that we really have to take seriously the possibility of continuing to use nuclear power, even using more nuclear power in the future, unless we really want to change our way of life or decrease the amount of energy we use significantly. So that's because despite issues with radioactive waste at the end of a fuel cycle, the greenhouse gas emissions that are traced to nuclear power are very small compared to the fossil fuels, which are the other big ways that we generate electricity today. So we're going to keep that in the mix as we go ahead. And we might be able to talk in another session about newer and safer technologies for exploiting that resource. But for now, let's go back to our traditional, more familiar renewable energy sources that can help us on a large scale. And those are solar power in the form of photovoltaics. Those are the panels, the dark-colored panels that just by sitting in the sunlight turn that solar energy directly into electrical energy. That's one way to make solar power. It's a very nice way, very flexible. These are solid state panels. They continue to be improved. They get cheaper to manufacture every year. So they're already very economical in a lot of situations. They're very flexible in the way that they can be used. You can have a big group of them, as on the previous slide, all together and manage the flow of electricity on sort of the utility scale, where a utility company controls how that gets put into the grid. Or alternatively, the solar panels can be located very close to exactly where the demand for electricity is, like on your roof or a sheltered parking lot at a company or a campus. Michigan State's doing a lot of these. We have a lot of solar panels on Sangren, the new Sangren Hall roof, in case you haven't seen those. Not much maintenance required once you get them going. They get them installed. They last for many years, and so very good technology. There's another way that you can harness solar power that has some advantages. If it's well done, you can actually harvest more power per solar incident area with a concentrating arrangement using the heating up a fluid as shown here. Reflector helps concentrate the heat energy from the sun onto some pipes with some fluid in them, maybe molten salt as in this example. Other working fluids are used, and you can use that heat to turn a turbine in the usual way and turn an electric generator and produce electrical energy that way and feed the grid. This example, these kinds of plants are always at the utility scale. They have to be at the utility scale. They wouldn't be very practical on a small scale. But you have big fields like this that instead of being solar panels are these concentrating troughs. And here's an example that's operating right now in California at I think 165 megawatts of capacity on a clear day. Besides generating electricity with solar power, you could also use the heat directly. Again, in this case, that would be usually better on a smaller scale, where the heat is needed for domestic hot water or some space heating. Domestic hot water turns out to be a very practical use for solar thermal, because there's no inefficiency associated with converting the energy into different kinds. The sun's light can heat the water that you're going to use directly, and you've done it. That's all that you need to do. And so we certainly envision some of that continuing. But again, it's going to be on a fairly smaller scale. Not every home will be able to use it. Not every building will be able to use it. And in the grand scheme of things, the amount of energy used for hot water, domestic hot water heating, is not a huge part of the total, but it's there. Here are just maps of where the solar resource is located. It's not surprising. It's in the southwest where the weather is favorable, skies are clear. Not so much here where it's always cloudy, or much of the northeast. Just a slightly different picture if you need the direct sunlight for the concentrating solar plant, but it's basically the same. So we don't need to spend any time on that. Let's go to the next one. Wind power, again, hopefully somewhat familiar to you. Fairly simple procedure. Build a turbine with big blades. When the wind blows, it turns the blades. Blades turn a generator, and you make electricity. Towers like these are becoming common across the Midwest. They can take up a little bit of the farmland, and the farmer can continue to grow crops around the sites. The towers, they have to be spaced out so that they don't block each other anyway. Offshore wind power can also be a big benefit. You don't have to worry about how the land would have been used if you have an offshore tower. You also get the benefit of very steady winds, usually better, more reliable and stronger winds offshore, where there are no obstructions to the wind depending on the direction. You don't want to go too far offshore because you have to bring that power back to land where the grid is, where the electric need is. But usually the extra cost of building in the water and transporting that energy, if you're within a few tens of miles of the shore, that's compensated for by having the extra wind available. So both of these siting methods are cost effective right now compared to other kinds of electric power energy sources. So this map shows where the wind is easily available and harvestable. Not surprising, it's in the Great Plains, so that's nice that it's a little bit different from where the solar energy is concentrated. And then we have our shoreline areas, also including the Great Lakes, I make note here. but especially the West Coast and the upper East Coast, and a little down here, the tail of Texas. All right, so this slide is going to hint at some of the difficulties, some of the challenges that are going to be present if we want to move in this direction. And one of those is that the location of where these renewable resources are harvestable doesn't match well with where the demand is for the energy. Now, for the demand, I'm just going to substitute where the people are, because that was an easy map to find. And here's a map on the lower right of the population density in the United States, and that's mostly where we need to have the energy available to use. And it doesn't match very well with where the solar energy is concentrated, or even where the wind energy is concentrated. The exception is the offshore wind resource on the West Coast. That isn't very far from a lot of people living in California and in the Northeast, where we have this offshore wind potential here. That's pretty close to a lot of population here. But the population here, down here, and even in Florida, will have to get their power. If their power comes from these renewable resources, it's going to have to be transmitted over fairly large distances. And that can be an issue, which we'll talk about maybe in another presentation, more detail. There are other kinds of mismatches that we need to take into account that are going to contribute to the difficulty in implementing this scheme. So the geographic one I talked about, and that's because at least if we're talking about electric power, you lose a percent maybe every 100 miles. If you have very high voltage transmission lines, sometimes it's more if you have older power lines. We're going to have to probably upgrade the grid to reduce those losses, because right now going halfway across the country is not very practical, and it's a bit wasteful. There are also time-based mismatches. The demand for energy changes during the day. It's less at night and more during the day. That one's pretty predictable. There are changes in demand with the seasons because of air conditioning and heating needs in the winter and summer that aren't so great in the fall and spring. But if we're talking about renewable energy, there's also changes, daily changes. Obviously, the sun isn't shining at night. It's only giving us solar power during the day. And the winds change with the seasons. So all these things are going to have to be taken into account. Some are fairly predictable, others are less so. The weather can have a big effect on how much energy we're taking in from these renewable sources, but we can't predict the weather with confidence more than several days ahead of time. And we need to be able to know. I mean, right now we know with good confidence how much power we can provide from a coal-burning power plant based on the stockpile of fuel, but we're not going to have that knowledge if we're relying on solar power, for example. There are also some unpredictable aspects on the demand side, people's behavior, industry schedules. Some of it's known, but we're not used to, the utility companies are not used to having to know that in very much detail, because they just make sure they have enough energy available for whatever the demand would be. So what we're envisioning is really a new way of doing things. What is it going to look like if we could really go to a minimal greenhouse gas energy future? I mean, the thing we have to do this is to stop burning fossil fuels. That's what creates most of the greenhouse gases that we're worried about. Now, as we've seen, the best, most practical technologies for getting energy without greenhouse gas emissions are also good at generating electricity. And electricity is a very versatile form of energy. You can use it for lighting, it's easy to use for heating, for cooling with air conditioning, that's electrical. You can do mechanical work of all kinds with motors. So our vision is that we use the next 30 years to convert any big energy users that don't already use electricity, we convert them to be able to use electricity. So obviously then we're going to need to have more electricity available for them to use. So we're going to have to build more wind turbines and solar power facilities as fast as we reasonably can. And then as these come online to supply the grid electricity, then we have to retire the coal and the gas-fired power plants that currently supply electric power to the grid. Natural gas is a cleaner and more efficient fuel than coal, so the priority would be to get rid of the coal plants first, and this is already happening to an extent, to a degree. And then we can save the natural gas plants for last. Probably in reality, we would even keep them in operational state even beyond 2050, even if we were get to the point where we can satisfy most or all of the demand by renewable sources, we probably still need to keep these natural gas plants in reserve for bad times, extended overcast or cold or extremely hot times. We might need some peak power capability and keep some reserve of natural gas capability for that reason. I think to make it easier for us to deal with the intermittencies, the unpredictability of the renewable sources, it's probably prudent to actually increase the baseline generating capacity from nuclear power plants. So I would envision over the next 30 years, some of the old nuclear plants will probably have to be shut down anyway. We need to be ready to replace them with new and better nuclear generating plants. That's going to take some time and some research, but from the physics side and the engineering side, this is definitely possible. There are some good possibilities out there that could be available in the next 30 years. All right, so one of the difficult parts of this is the transportation sector. You might not remember from the flow chart way at the beginning, but transportation is a big part of all the energy we use. It's about 28% of the total energy input for the United States at this point in time. And we've seen that our renewable sources are good at making electricity, but at first glance, the way you usually supply electricity to a user is with wires. Okay? So how do you do that with vehicles that have to move? That's a bit of an issue. Okay, the obvious answer is that we're going to use storage batteries, but how much can we really do? So let's take a look at this in a little bit more detail. Here's how the energy used in our transportation sector is broken down into various pieces, various parts of the transportation picture. And this is pretty self-explanatory, I think. The major part of this pie, the major fraction of the energy used in transportation is for moving people around in their own individual vehicles. I'm not going to distinguish between cars and light trucks. A lot of the pickup trucks that are out there are just used for basic transportation also. So those kinds of road-going vehicles, that's already almost 2/3 of all of the energy we use, all those trips we take. We like road trips and things like that. Then there's trucks of various kinds over here, And I'm distinguishing between the sort of medium-sized, bigger than pickup truck, delivery trucks and things that move around mostly in cities, and the bigger tractor semi-trailers in this slice that are going between cities, mostly long distance freight hauling. I've combined buses and other mass transit systems, some of which are using electricity already. It's a fairly small fraction of this, but when you think of the L in Chicago and subways and things like that, those are all electrified because they can take their electricity from the tracks. They're on fixed routes. And there's that. And then we have other trains, the Amtrak and the freight trains, the diesel trains, which are not electrified even though they're on tracks. They use fossil fuels at this time. And then we have up here all the aircraft, which is a mix of air cargo, private aircraft, big jet airliners, and then at the top all the maritime ships and boats, some of which are ocean-going vessels that are also taking big cargo. Okay, so electrifying this is a bit of a challenge because you can't run a big extension cord to all of these vehicles, but recent advances in particularly lithium-based batteries, is really helping us out. And it turns out that some of you may be aware, but we're kind of at the start of a revolution already in electrifying our transportation. There are now affordable electric vehicles. You may have heard of Teslas. Tesla, for example, or the Chevy Bolt, or others that are out there and available right now. And they have a lot of advantages. And so on the technical side and the practical side, it looks to me like that 63% of the energy that was over here in this big blue section on a 30-year time scale, it's not hard to imagine virtually all of this being converted over to electric power through batteries, through storage batteries, either based on the current lithium batteries or a future battery technology that's even better. Battery technology is continuing to improve both in energy density, longevity, and cost to manufacture. So these are going to keep going, and I'm pretty sure that can be self-sustaining. That shift can be self-sustaining because if you ever try an electric car, you see a lot of advantages. The advantages include the total cost of ownership because electricity is cheaper than gasoline. Maintenance is very low, reliability is very high, and the driving experience is very pleasant. No vibration, very little noise. All these advantages, I think, will overcome the disadvantages in cost up front, which is going to be decreasing, and the range and charging speed issues, those will be dealt with. When you get further around on that pie, you get more difficult, more challenging situations where you need longer range and more energy, like the long-distance trucks and the ocean-going cargo vessels and the aircraft in particular. Big aircraft are not going to be able to carry very heavy batteries with them, and they need a lot of energy. So the bottom line for us is that we actually don't think we'll be able to get rid of all fossil fuels in that transportation sector by 2050. I think that's just a bit too soon, a little bit too much to ask. So our scenario is going to retain at least about 8 quads of energy coming from fossil fuels to devote to the transportation sector where it's still going to be needed. But the rest going to be rechargeable batteries, and it'll take their energy from the electric grid. That's our projection. Okay, on the rest of the picture is, like I said before, except for that and some heat energy taken by ground sourced heat pumps and solar thermal collectors. Everything else we're going to try to do with electricity. And then we're going to supply the electric grid with renewable sources. And that means the electric grid itself is going to have to be bigger. It's going to have more capacity. It's going to have to be able to transmit energy over longer distances. That'll help us utilize the solar energy and the wind energy where it's most practical to harvest and get it to where it's needed. And if we have long distance transmission capability, that'll also help us with the intermittency, with the fact that the sun isn't shining here right now. It is shining someplace else. At the same time that if it's cloudy here, it's sunny someplace else. We can move that power around. We'll be in good shape. So, given all that, and to do it in 30 years, here's how it would look graphically. Okay, so time on the horizontal axis, and then I've stacked the various energy sources on the vertical axis using quadrillion BTUs of energy, the same energy unit that was used on our first energy flow diagram. Here's a slight increase in nuclear power. Here's that residual 8 quads of petroleum. Here's coal and natural gas going away, pretty much. Biomass, not changing much. Not much more change in hydroelectric. The geothermal is too small to see. I've omitted it completely here. And then we're ramping up the wind power and the solar power from their small current contributions to significant final contributions here. Now, it looks like I'm advocating that we use a lot less energy in 2050 than we use now, today. But that's really not quite the case. That's a little bit deceptive. And here's the reason why. I'm actually, in my model, we are projecting an increase in the energy used, even though we think that conservation and better efficiency in all sectors will help us make better use of our energy sources. We still think that we still want to allow for economic growth, population growth, doing more things, having better quality of life for everybody. So this is actually a scenario that includes economic growth and more energy use. The reason it doesn't look like it here is because there's a large amount of wasted energy associated with combustion of fossil fuels. So the way that the chart is usually accounted, the input side of the chart is how much fuel you have to put into the system. But you have to realize that only 20% or less of that energy comes out as useful work at the end, and a lot of it just becomes heat energy. Goes up the chimney or the smokestack or whatever, has to go into the cooling pond, and that's not energy we can use. It goes out into the environment. So we call that rejected energy or inefficiency or things like that. And let me go to this one. That was accounted for by these gray bars in that original 2018 data of how we use energy. So whenever there's a lot of combustion here, a big fraction of the energy in is rejected. So that applies to transportation as well. So most of these electric generating plants are burning fuels, and so a lot of the energy isn't available to use. Less than a majority of it is available to use. And that happens in industry that's relying on combustion of fuel oil, and natural gas. And that happens in transportation. It's even worse in transportation because the internal combustion is even less efficient than the kind of combustion you can do in an electric power plant. So a lot of energy gets lost. If we're not depending on coal and natural gas and petroleum, this amount of energy is a lot less, and that's what leads to the proportions we saw on my chart. Okay, so there's a whole bunch of rejected energy over here that's no longer being rejected, because when we count solar energy, we just count all of it as being on the input side, and you don't have that combustion loss. And the same with wind. We do have some of that inefficiency with nuclear, because the core has to be cooled, and there will still remain some with the petroleum that's used in our transportation. Okay, so I'm including that. So here's a revised and simplified energy flow diagram for our projected 2050 state, where now we're supplying the electric grid with a lot of renewable and nuclear energy. And this rejected energy is much smaller. There's still some from the nuclear plants. There's more now from transmission, transmission and distribution of the electricity. I've counted that into this rejected energy here, so as to be fair. And there's still some in industry, and some if you're burning wood, if you're burning biomass, you got some rejected energy here, but it's going to be smaller. And so that's our scheme. That's our sort of vision, bottom line. I think it's doable. It's not going to be completely easy, but there is a way in principle to supply all of our energy and more with much less greenhouse gas. This 8 quads of petroleum that's still here, that's less than 10%. That should mean that our greenhouse emissions have been reduced by 90% at this point, if we get close to this scenario, and then we can still work to make improvements. But that would be significant, we think, compared to where we are today. Okay, so it's not going to be easy. Hopefully next we'll have another session available to you soon that will discuss the obstacles. What could those obstacles be? Well, we're going to have to make a lot of wind turbines and photovoltaic panels. Is that possible and practical with our manufacturing capability at this time? We're going to make a big expansion of the electric grid, do it in a smart way and with an eye toward efficient transmission over longer distances. Technically, I think that can be done, but it's going to be a challenge, probably. What about the energy storage? We're going to need probably some energy storage. If we don't want to overbuild, we're going to be working really hard to build as many wind turbines and PV panels as we can. We don't want to have to build more than we need. So that means we're going to have to be able to store energy at times when the sun's not shining and the wind's not blowing, to be able to use later. And that's going to be a big change. Lots of capability that we don't have yet. How to do that is a potential challenge. And then it's a whole new way of doing business, I think, for the utility companies. The way they do it now, they are striving to try to even out the load, try to make the load the same all the time, the demand the same all the time, by encouraging off-peak demand and things like that. And then they can just set their supplies to a certain level and set it and forget it and run like that at constant rate of supply and demand. but that's not going to be the way of the future in this scenario. They're going to have to be able to manage the changes we talked about with weather and the seasons and the time of day and how much wind there is. They're going to have to be able to deal with that and manage storage when they have excess generating capacity, and using stored energy when they don't have the capacity, and predicting demand and all these things. It'll be that's a potential challenge as well.